All right, two last little things about Chapter 7. Universal gravitation. You see, there was this guy named Isaac Newton who come up with this little thing here that any two objects with mass attract each other. Now, most of the time we don't think about this, but like even if it was you and me in a conversation with each other, it's like, hey, oh wait, gotta draw the beard. I kind of look a little Amish there, but anyway, hi, I'm Mr. Cole. And then you'd be sitting here, and you'd be like, hey, this is kind of pointless right now. Hey, I'm, Stan. And we'd be like, hey, Stan, I'm Mr. Cole. And you're like, hey, I'm Stan. Anyway, in theory, this is so stupid. In theory, there would be a gravitational attraction between us. Now, we do not really notice this gravitational attraction between us because of one thing. My mass and his mass are probably both pretty small masses. So this force would be pretty... Hey, we can actually calculate it. I didn't even thought about this. I was planning on doing two balls up here and their attraction to each other. But let's say that my mass is... I'm like 102 kilograms. So there's a little bit about me. And let's say that Stan's been hitting the gym. He's pretty lean. Let's go with Stan's about 85 kilograms over here. You can at least add a kilogram to me because of the beard. But anyway, so there's kind of where I come in on this one. So let's say that me and Stan are having I don't know, Stan could be a close talker. Yeah, let's say Stan's a close talker. Not really into that, but anyway, let's say that Stan is, let's make an easy number. Let's just say 1 meter away from me. So there's me and Stan. In theory, we are attracted. Now here's the equation. Newton's law of universal gravitation. This force is nothing but big G, M1, M2, over R squared. Now, some books will do big M, little m over R squared. It doesn't matter. I guess if we did big M, little m, then I would, by default, be the big M in the equation. The only thing in this that should look remotely odd to you is the big G. This big G, it's a guy named Cavendish come up with it after experimentation. It's just a gravitational constant is all big G is. Let's see, big G, I don't even use it a lot. What was it, like 6.6, I can't write, 6.67 times 10 to the negative 11. The unit is a crazy looking unit. It's like a Newton meter square, kilogram square. And if you're wondering how did I figure out that unit, well, I did it by looking at the equation, because it's going to be a Newton times a meter square divided by a kilogram square. So anyway, there's the unit for big G. So if I want to find the force of attraction between me and Stan over here, forget, this sounds a little awkward to say Stan. Let's cancel that out. Me and I cannot think of a girl name off the top of my head. Crap. Maybe I'll just keep it with Stan. It's better that than trying to think of some other name. Sorry, I'm good at physics, lousy at thinking. That don't make sense either. Anyway, let's just plug in numbers. Big G times me, 102. Old Stan's there, 85. Separation, 1 meter between us. Now notice I just wrote big G because I'll be honest, I'm too lazy to write 6.67 times 10 to the negative 11. However, I will type it in my calculator. 6.67, 10 to the negative 11. Let's close this down. Well, I didn't have to do that. Times 102 times 85 divided by 1 square, which was a little pointless. But anyway, the force between me and Stan, according to my calculator, is 5.8 times 10 to the negative 7 newtons. This is why we do not notice this force of attraction. But it is there between any two objects. The most common problem for you to kind of end up doing is a problem like this. Or, let's say, another, alright, here's a couple of types of common things. One, this would be a big one. Here's the sun. Here's Earth. And a lot of times you work problems where they want you to try and calculate this Earth-Sun force. Now, this is actually a sizable force. Why? Because both of these objects are so large. That's your reasoning behind that. It's funny, I know the mass of a lot of things off the top of my head, but I don't even know the mass of the sun off the top of my head. But anyway, sometimes you'll have, like, here's the moon. Sometimes you'll have the same problem trying to work out between the Earth and the moon because the Earth or the moon is rotating. So these problems usually involve, like, rotation. Now, one of the big things we can do is this. Let's go back to that Earth and moon again. So like here is planet Earth. So there's Earth, home sweet home. Over here is the moon. Probably drew the moon a little bit big. Anyway, so here's Earth, there's the moon. The moon is in rotation and orbit about it. What holds the moon in orbit? Why does the moon move in a circle? Oh, wait a second. The moon's moving in a circle. mv squared over r should be the first thing pops in your head. Why does it move in a circle? It's because of this attraction to the Earth. So big G is equal to, I'm going to write big M, little m over r squared. Where big M is going to be the Earth, little m the moon. And so that cancels out. And we've kind of got a little bit going on here in this problem. Let's see. That r cancels that square. I don't even know what I'm finding here, but I've got big G, M over r equals v squared. So anyway, oh, you know what's actually neat about this where we've got down to? You can actually use this to solve for a black hole. Because in a black hole, you've got this same situation kind of going for a black hole, but what happens is this mass is so big that light can't even escape. So in the case of a black hole, we'll rewrite this. Big G over M over R equals c squared. If you substitute in the speed of light for your velocity, you can actually find there's a name for this in the world of black holes. So I'm going to write around this. There you go, black hole. Black hole. And what happened is the mass is so big that light can't even escape the gravitational pull of the central mass. And there's actually a name for this. I'm not going to try and spell it, but it's called the Schwarzschild radius. So you can actually find the radius around a singularity. In other words, a point in space with a mass so big that light can't even escape. And if you want to know more about black holes, then, well, somebody else can make a video on that because it's not like something I need to take time for. But anyway, this gives you a little bit of reference on this. Now, I do want to throw one more thing at you, other than this whole big G thing. And a very common thing that happens is this. You'll work a problem, and it'll give you the time for, like, the moon to rotate around the planet. And you'll be like, crap, why did it give you time? For one simple thing. When you do your mv squared over r, rewrite it like this. M, and instead of v, do distance over time. Circumference over time. And there's the big trick in that problem. Anyway, this is just some little fill-in stuff I was just adding in to this chapter. But anyway, good luck and happy test taking.